Hi everyone. Today we will discuss elastic as well as inelastic collision. So here you can see two bodies are said to impinge directly when the line of motion of each is along the common to their surfaces at the point where they touch. So let us say this object and this object, they are moving and they are colliding. So here this becomes your common tangent to this object as well as this. So now the line of motion of each is along the common normal to their surfaces. So this is the tangent, common tangent. So this will be the common normal. So this object as well as this object, it is moving along this line. Now either it can move in the same direction, it can move in the opposite direction. Suppose these two are moving in this direction, or they can move in the opposite direction. One is moving this side, another is moving this side, so they can collide. So this is the line of motion or the line of action, this as well as this. And when they collide, it means this becomes your common tangent, and perpendicular to this or normal to this, we have this line of motion or line of action. Now here, this collision, it can be along the same line or it can be an oblique collision. So suppose one object is coming from this side, another object is coming from this side, and they collide somewhere here. Okay, and after that, again, direction of motion after the collision, again it can be in two different directions, this side or this side. So it depends, it can, one can move in this direction, another can move in this direction. So all this depends on the momentum that is being imparted by one object to the another object. So here either we can have this oblique collision, either along this one object is moving in some inclined surface, along inclined surface, another object may be moving along the horizontal surface or along the horizontal line. So, or both the objects, it can move along the inclined line or the oblique line. So any situation can happen and the collision will take place. The common normal to the point of contact. So here you have this point of contact, and this is the common normal. Is called the line of impact. Line of impact, or the line of motion through which they are or along which they are colliding. Now there are certain principles or certain laws under which these collisions are guided. One is your principle of conservation of linear momentum. Now as far as the collision is concerned here, if you consider this, these two objects are colliding, there are no external forces acting on the system, because when this object collides with this object, let us say in this, and they come and they collide, okay. So or suppose here it is moving this side and this is moving this side, here it is moving with u1, u2. If u1 is greater than u2, obviously there will be some collision somewhere, if u1 is greater than u2. It means the only force experienced during the point of collision or during the moment of collision, here if these two collides, so only force acting between these two at the time of collision, it will be force of interaction between these two. There is the force of contact or force of interaction. This will be apply force on this, and this will apply force on this. This will be this side and this will be this side. Just because of the collision, instantaneously a force will get generated, and that will act to each other. That will be mutual force of impact, you can say, the mutual force of impact. This will apply force on this, this will apply force on this. That will be an internal phenomena, and summation of that force for this common surface, that becomes zero, because summation of all internal forces, it is zero. So summation of force experienced by this due to this, or experienced by this due to this, that will be zero, because it is an internal force. So there are no external forces acting on the system. When there are no external force acting on the system, or summation of all external forces acting on the system, it is zero, the momentum remains conserved. So this principle acts as far as the collision is concerned, and that's why under this principle we say that the summation of momentum before collision and after collision, it is equal, because momentum is a conserved quantity. So summation of momentum before collision or after collision, it will remain same. So that concept we get from the principle of conservation of this linear momentum, and this principle we are able to use just because no external forces are acting, or summation of all external forces acting on the system, it is 0. So we will be able to use this principle. Second is, when two bodies collide, the only force acting on them at the time of impact is the mutual interaction. That's what we have. This is the only force, mutual interaction. The force which gets generated due to the collision, when they collide with each other, when they come in contact with each other. So that is the only force, mutual interaction, which acts along the common normal. We say common normal because this is the tangent, common tangent. So this becomes your common normal to this surface or these colliding objects. There is no force acting along the common tangent, hence there is no change of momentum in that direction. That's why we say the momentum remains conserved, and when momentum remains conserved, summation of forces before collision, sum of momentum before collision and after collision, that remains same. Now the third law, which is also termed as Newton's experimental law or simply Newton's law on collision. Either you can say Newton's experimental law or Newton's law of collision or law on collision. It says that when two bodies impinge directly, and when two bodies collide directly, the relative velocity after collision bears a constant ratio to the relative velocity before collision. So suppose velocity of both the objects, this object and this object, let us say it is u1 and u2 before collision. After they collide, their velocities becomes v1 as well as v2. Okay. Now if two bodies collide obliquely, so this is in case of straight line motion, and they are moving along the same line. Now if two bodies collide obliquely, their relative velocity resolved along their common normal. Relative velocity resolved along, because once they collide obliquely, there will be two components of velocity, one along the x-axis, another along the y-axis. So if you take one of the direction, okay, which is along their common normal, after collision bears a constant ratio to the relative velocity before collision. So here also this law is applicable. The only thing is we consider that along the common normal after collision. The constant ratio depends on the elastic property of the material. It depends on the elastic property of the material of the two bodies, but is independent of their masses. It has nothing to do with the masses, it only depends on the nature of the object, whether it is inelastic, elastic, or how much elasticity is there. It is denoted by the letter E, this is small e, and it is termed as coefficient of restitution. So this is termed as coefficient of restitution. So here, as I was discussing, initial velocity, suppose u1, u2, that is before collision. After collision it is v1 and v2. Then how we consider these statements, that you can see. The relative velocity before collision, it will be how much? u1 minus u2. After collision, if their velocities are v1 and v2 here, and this you can consider. So it will be v1 minus v2. After collision, the relative, it will be v1 minus v2. Before collision, it is u1 minus u2. Their ratio is always constant, and that is equal to negative of this is minus of E, where E is termed as your coefficient of restitution, and that coefficient of restitution E, it depends only on the elastic property of the objects or the masses in general. It does not depend on the mass value. Now depending on this value of this E, the quantity lies between 0 to 1. This lies between 0 to 1. It is always positive, and either it can be 0, it can be 1, but it is not beyond this interval, lies between 0 to 1. Now when E is equal to 0, the collision is perfectly inelastic. Here we use the word perfectly inelastic. Perfectly inelastic when E is equal to 0, the collision is perfectly inelastic. When E is equal to 1, the collision is said to be perfectly elastic. And if E lies between 0 to 1, excluding 0 as well as excluding 1, somewhere between 0 to 1, then it is a case of inelastic collision. So we have three types of collision, you can say: perfectly inelastic, perfectly elastic, or simply elastic, and inelastic collision. So either inelastic or elastic, and the third is perfectly inelastic. So perfectly inelastic, it is when E is equal to 0, perfectly elastic or simply elastic, okay, when E is equal to 1, and if E lies between 0 to 1, then the collision is said to be in general inelastic. Now depending on all this, as we have already discussed, when summation of all external force is 0, summation of momentum remains conserved. So momentum, again, it is a vector quantity, so we can resolute it. It means summation of momentum along x-axis is conserved, summation of momentum along y-axis is also conserved. Now if it is a case of elastic collision, then apart from momentum, the kinetic energy also remains conserved. So this is applicable only for elastic. Momentum is conserved whether it is elastic, inelastic, perfectly inelastic, and so on. But kinetic energy remains conserved only if it is a case of elastic. So this principle or this rule you can't apply before knowing whether it is a case of elastic or inelastic, or if it is exactly known to us that it is a case of elastic collision, then we can use momentum conservation principle as well as kinetic energy conservation principle. Otherwise, momentum conservation principle is applicable in both type of collision, elastic as well as inelastic. Now from this Newton's experimental law or Newton's law of collision, we got V1 minus V2 upon U1 minus U2, it is equal to minus of E. So this we can use for specific purposes. So here you can consider direct impact on a fixed plane. So suppose you have this fixed plane and a ball is dropped. So here the second object is fixed, that is always at rest before collision as well as after collision. So when ball is dropped, it will rebound. Again it will drop, again it will rebound. So this process keeps on going. So second surface or second object is always supposed to be at rest before collision and after collision. Only one object is moving. It is moving down, it is moving up because of its rebound, again moving down, moving up, and so on. So we will see what happens and how this rule can be applied to simplify problems related to this situation. So if second object is at rest, suppose this is at rest and this object is only moving, so V1 minus V2 upon U1 minus U2, and that is minus of E. So here if we consider V1 is equal to V and V2 is equal to how much? 0, because after collision this remains at rest. U2 is equal to how much? Again 0. Before collision it was at rest, after collision also it is at rest. So can you say that V by U it is equal to minus of U? After collision, velocity of this object becomes V and before collision it was U. We are now generalizing. So V by U it is equal to minus of E. So you can say this V by U is equal to minus of U. This is the velocity of this object before collision. This is the velocity of the same object after collision, because second object always remain at rest before as well as after. So this as well as this will be 0. So from there we get a general relation V by U is equal to minus of E. Now let us see how to use all this concept. So suppose a body is vertically dropped to the fixed horizontal surface from a height h1 above it and rebounds to a height h2. Now let us consider this case. This is the ground surface or a fixed surface, you can say. A particle is dropped from, suppose this, from a height of h0. The initial height, it is h0. Either you give this height h0 or you say it is dropped with this much of velocity. So initially it is dropped from that velocity. Either we can give the velocity or through which height it has been dropped we can give. So from that we can calculate. So it is dropped from a height of h0. Then it rebounds to a height h1, that is after collision, after first collision, then rebound to a height h2 after the second collision, and so on. So before the collision it has been dropped from a height of h0, first collision happens and it rebounds to a height h1, second collision happens, it rebounds to a height h2, again the third collision, fourth collision, and so on. So let us now analyze this. V0 is equal to how much? This is the velocity just before the first collision. Then it has been dropped from the height h0. So now it will collide. So just before the first collision, it has covered a distance of how much? V0. So using the simple kinematic equations under gravity, you can calculate V0 is equal to square root of 2g h0. That is V square is equal to U square plus 2gh. You can consider that u as 0, and from there v square is equal to square root of 2gh. In general, h is equal to h0. So with that we get this relation. So this is the velocity just before the first collision. Now after the first collision, it has rebound up to this height h1. So velocity after gaining this height h1, that will be equal to how much? Square root of 2gh1, means after collision it has acquired some velocity, suppose v1. So with this velocity v1, it has started moving up, that is against the gravity, and up to covering this height up to h1, it will come to what? Rest. So initially it acquired some velocity after collision, moved up to a height h1, and then come to rest. So from that again v square is equal to u square minus 2gh. That relation, initial velocity here, let us see, it is v square, v, here it becomes 0, putting u as 0 there, you can calculate and you will get v1 is equal to square root of twice of gh1. Similarly, you can calculate v2, because here it becomes h2, so v2 is it will be equal to how much? Square root of twice of gh2, and so on. So that way we can calculate v0, v1, v2, and so on. Now let us use this Newton's law. So v1 minus v2 upon this, it is equal to minus of that E. So if you use this relation, v1 minus 0, because the second object is at rest, divided by v0 minus 0, square root of twice of gh0, square root of twice of gh1, this was before the collision, and that is equal to this E. Here we are taking this magnitude of E, so that it is always considered to be positive. So v1 minus 0 upon v0 minus 0, so that is E, because u2 is 0 and v2 is also 0. Putting these values, we are getting this relation. So if you simplify this, if you simplify h1 upon h0, that will be equal to how much? E square, because replacing the value of v1 as well as that u there and squaring both the side, you will get h1 upon h0, that you can see here. v1 upon v0. Okay, so v1 upon v0, but v1 is equal to how much? Square root of 2gh1. This is square root of 2gh0. Squaring both the side, that square root will be over 2g, and 2g that will get cancelled. So h1 upon h0, that will be equal to how much? E square, because we are doing the squaring both the side, that will be E square. And from there, you will get this relation h1 upon h0, that is E square, or h1 is equal to E square h0. Similarly, h2, again if you see the height covered after the second impact, again squaring both the side, you will get h2 is equal to E to the power 4 h0, and so on. Similarly, if you replace by the time equation, V1 upon V0, so V is equal to U plus GT, so U it will be 0, so from that you will get GT1 upon GT0, that is equal to E. So time taken after the first collision, if it is suppose T1, then T1 is equal to E times T0. So T1 will be equal to E times T0, T2 it will be equal to E times this T1, T3 it will be equal to E times T2, and so on. So from this you can replace this T1. T1 is equal to E times T0, that is the initial time taken when it was dropped with the initial with some velocity from the height h0. Similarly T3, that is E T2, and so on. And this way you can calculate. So here it will be how much? Hn. From this you can consider Hn, height covered after the nth collision. So can you say after second collision it is E square whole square h0. So when it is second collision it is 2. So nth collision it will be how much? E square to the power n h0. So this way we can calculate height covered after nth collision. Similarly the time taken after nth collision, and so on. So T2 is equal to E T1. So if you replace this E T1, T1 is equal to E T0. So this becomes again E square T0. Okay, E square T0. So after second collision, time taken is E square T0. T0 is the initial time taken when the first when the particle has been dropped from some height h0. So after nth collision, can you say time taken it will be E square. So it is E to the power second collision. So here it is this. So E to the power n T0. So that way, so here it is E square to the power n, here you are getting simply E to the power n T0. So we can calculate the time taken. Similarly we can calculate height covered after the nth collision, and so on. This you can verify here. T3 E T2, so E T2, T2 is equal to E T1, so it is E square T1, and T1 is equal to how much? T1 is equal to E T0, so it becomes E square E T0. So this gives you EQ T0. So third collision we are getting E3, second collision we are getting E2, so nth collision we will get E to the power n, and similarly we have this height covered and all that. So this way we can calculate it. You may keep this relation in your mind just for quick calculation of the questions based on such concept, this as well as this. Or if you forget, then it is a simple derivation. You can just use the laws of motion, substitute the velocity expression depending on height covered, or the velocity expression depending on time covered, substitute it, and you will be able to calculate all this. Thank you. We will continue the problems based on these concepts in the next video. Thank you.